Welcome back to the fifth installment of Waves, Light, Sound. Alright, so moving on, the mirage. During the day, the temperature of the air directly above the surface of a road increases due to conduction of heat from the asphalt. A ray of light from low in the sky will refract away from the normal as it enters the hotter, less dense air. The deviation continues until the ray is totally reflected just above the road. It is then continuously refracted towards the normal as it enters the cooler, denser air above. An observer receiving this ray will see a virtual image of the sky and may interpret it as a pool of water. And here it is. See? Now, relation between critical angle and refractive index. Relationship is such that sine C, which is the critical angle, so the sine of the angle of the sine of the critical angle is equal to 1 over the refractive index. Okay? So one of the angles is 90 degrees and the other is the critical angle, and we all know that sine 90 is actually 1, so you just get rid of the sine 90 under here, right? And the critical angle is always in the medium in which the wave travels with lesser speed. So the more dense the density material is in which the light is traveling will be where the critical angle is for light. And this is the more optically dense medium, so the glass, the light. So note that if the critical angle or the refractive index of a material is referred to without mention of the second medium, it can be assumed that it is relative to it. So you could actually do an experiment where you play with light and determine the critical angle, and then from there you could determine the refractive index. Without doing the refraction of light multiple times, you could determine the critical angle inside of that block of glass, and then you could solve for the refractive index. That sounds cool, right? Now, optical fibers work based on light being totally internally reflected within it. Again, optical fibers have the following uses. They have telecommunications and in endoscopes. And from endoscopes, you can use them for diagnostic imaging and therapy. So if you look in here, you would see this is an example of optical fiber and some light being passed through it, which is totally internally reflected. And basically this light is trapped in here, and that is how it's able to shine light in those long rods, right? Science is great. So a mirror reflects only about 90% of the light incident on it. Right-angled isosceles triangular glass prisms are used in many optical instruments such as periscopes and binoculars to reflect light. When light enters the prism perpendicularly through one of the shorter sides, it meets the opposite wall at 45 degrees. This is more than the critical angle of glass, which is 42 degrees, and therefore there is total internal reflection. So here we have reflecting prisms. So going through the shorter sides, it turns through. So this is 45 degrees here to the normal and 45 out, and then this showing you how it works in a prism, reflecting prisms. So light here again, you could turn it such in a way that you don't need to use two, you could use just one. And in a periscope, you use it this way. Inverting prism using binoculars. Note how the incident rays are flipped when they emerge from the prism. Okay, so it just shows you how the prisms are used, and to show you the examples. You could use this prism to cause light to turn through 90 degrees and then through 180, and then you could just turn it in a certain way where it doesn't need two. Then it shows you how they're using periscopes and binoculars. Alright, so now we're moving on into lenses. So we're going to use the terms, we're going to look at the terms used with lenses. You have the principal axis, which is this very long line here running through the optical center, and then all of the rays of light will converge at something called the focal plane, and then the focal length is the distance between the optical center and the focal plane. This is a convex lens. With a concave lens, better known as divergent lens, we also have a principal axis. You have an optical center. The distance between the optical center and the focal plane is called the focal length, and the place where the rays seem to diverge from would be the focal plane right here, right? A lens is a piece of specially shaped transparent material that can form focused images of objects. A convex or converging lens is one that is thicker at the center. It can converge parallel rays of light to produce a real image. A concave or divergent lens is one that is thinner at its center. It can diverge parallel rays of light to produce a virtual image. The optical center O of a lens is the point at the center of the lens through which all rays pass without deviation, meaning they go through straight, right? So if you look at this, you'd realize if this is a ray of light, you realize it did not bend, so that's without deviation. Ray of light here did not bend without deviation. However, if you're not passing through the optical center, you're gonna bend depending on the lens used. So you're gonna bend for diverging, bend away, and for converging, bend towards the principal axis, right? Good. The principal axis of a lens is a line that passes through its optical center and is perpendicular to the faces of the lens. The principal focus F of a lens is a point on the principal axis through which all rays parallel and close the axis. The principal focus F of a lens is a point on the principal axis through which all rays parallel and close to the axis converge, or from which they appear to diverge after passing through the lens. Focal length of a lens is the distance between its optical center and its principal focus. The focal plane of a lens is the surface perpendicular to its principal axis and containing its principal focus. Parallel rays focus on the focal plane even if they are not parallel to the principal axis. In order to determine where the rays focus, draw an incident ray straight through the optical center to a point on the focal plane. Then connect the other parallel rays after passing through the lens to the same point. So if it's not the traditional straight across, and then you have the lens, and you draw this straight, and then you draw these from the center to combine with this. If it's not the traditional, suppose you have this and you have this. Suppose I give you a drawing like that. What are you going to do? Well, you draw the focal plane and you just match to this. Okay? Alright, so that's what you're going to do. Magnification. Magnification, M, is the ratio of the size of the image to the size of the object, where image height is divided by object height. Magnification can also be determined by the distance of the image from the lens divided by the distance of the object from the lens. So the image is the form and the object is what is real. Okay, the image is what is not real and the object is what is materialized, is actually real in your hand. So if you wanted to draw, if you want to determine the magnification of your hand, you could trace it, and then you could measure the length of your hand from here to here, the longest finger, if your middle finger is the longest finger, and if you divide the length of your hand, which will be the object, if you take the length of your drawing, which is the image, and divide it by the length of your hand, which is the object, you realize that your magnification will be 1, because you didn't make the drawing of your hand bigger, you made it the same size, so it'll just be 1, right? Now if you drew your hand double the size, then your magnification will be 2, right? So say your hand is 10 centimeters in length, and you went and you drew, you went and you drew your object 20 centimeters long, then your image will be 20 centimeters divided by 10, which will give you 2, right? Now real images are those produced at a point to which light rays converge. Virtual images are those produced at a point from which light rays appear to diverge. So examples of real images. Images produced on the retina are real images. Images produced in a camera are real images. Images produced on the screen at the cinema are real images. Virtual images are images produced in the mirror. So what you see in the mirror is virtual. Images produced by a convex lens acting as a magnifying glass is a virtual image, and images produced by a concave lens is referred to as a virtual image. So real images formed by a lens can be seen on a screen, are produced by the convergence of rays, are located on the side of the lens opposite to the object, and are inverted, meaning they're upside down. So the image that's produced on your retina at the back of your eye is upside down. Your brain is what turns it right side up. Now virtual images formed by lenses cannot be formed on a screen, are produced due to the divergence of rays, are located on the same side of the lens as the object, and are erect. So you, in that mirror, that image that you see in the mirror is virtual because it's upright, right? Constructing scale diagrams for convex lenses. So you have to learn how to draw scale diagrams. You have to learn how to draw them, and it's not hard. It just takes practice. So first you will start off with your principal axis, and then you will draw your lens. You have your optical center here, and what this shows is that you have your optical center, your principal axis. You always have a focal plane. You have a focal plane, and then you have twice the focal plane right here, our focal length, because this refers to focal length. So you have your focal length and twice the focal length. That would be the lens from, so twice this distance. So if this is 2 centimeters, then 2f would be 4. And it's showing you that any object outside of the twice the focal length will be a real image. Real images are upside down and on the opposite side of the lens. So it will be a real image, and it will be very small, and it will be produced between the focal length on the next side and the twice the focal length, right? If you have an object that is placed directly on twice the focal length, then you're gonna get a real and inverted image, right? Once it's real, it's inverted, and it's gonna form directly on twice the focal length on the next side. So this is something you would see that would be produced in a camera or in the eye, right? So something like that. And a projector, this is what usually happens. The object is between twice the focal length and the focal length, and the image produced is much bigger but upside down. And so in projectors, there's something in it which causes this to flip before we see it on the big screen. If you put an object on the focal length itself, there'll be no formation of an image on the next side. None whatsoever, because the lines, the rays of light will never conjoin. They just keep going and going. And you could try this at home as well. So if you put something between twice the focal length and, well, no, if you put it between the focal length and the optical center, you're going to get a virtual image. You're going to be on the same side as the object and larger, and it will be erect, right? So something like that, you know, this is what's going to, and this is what you would see with a magnifying glass. This is the only case where the image is virtual and erect. The distance of O from the lens must be less than the focal length. So yeah, so wherever, depending on where you put an object on whatever side of the lens, so once you know the focal length and twice the focal length, depending on where you put the object, will determine what type of image you're going to get. Are you going to get a real image or a virtual image? The virtual image is most definitely going to be formed in between the optical center and the focal length, and you'll get no kind of image at all if you place the object on the focal length itself, right? So you can go through these over and over and over again. So it's smaller, so characteristics of the image formed in a concave lens. Okay, so it's smaller than the object, it's closer to the lens than is the object, it's virtual and erect. Okay, so here we have the drawing. So using the divergent lens, this will be a little bit different. As you can see, we still have the straight line. We usually use two ways. So you have that straight line going from the top of the object, passing straight through the center of the lens. And I'm going to make a video with this at some later date, doing the drawings of red diagrams, so you could see how to do them. So here you have the straight line going through here, and then from the top again you have another ray of light that's going straight across, right? And once they go here, they diverge, and in diverging they pass through the apparent focal plane, right? This pass through, this crisscross, will then show you at what point you draw the height of the image. Now the height of the image, as you can see, is smaller than the object. On the other page, we're using convex lens. These are convex lens, and this is the only one that produced a virtual image, which was in the case of the magnifying glass. Okay? And remember, when you put the magnifying glass really close to the object, it gets bigger and bigger and bigger, right? That is the case there. And here's the lens formula that you can use. 1 over u plus 1 over v equal to 1 over s. So you have to remember what u, v, and f are. F is very easy to remember, it's focal length. U is the distance of the object from the lens. It's positive if it's real, and negative if it's virtual. V is the distance of the image, right? From the lens, it's positive if it's real, and negative if it's virtual. So you gotta remember what u and v are. So u is for the object, and v is for the image. Okay? And here ended the lesson on waves, sound, and light. I hope you enjoyed. I hope you understood what to do. And guess what? I'm gonna always be here unless something bad happens to me, or time takes away what I love to do. So look out for the handiwork on red diagrams and stuff like that, which will be at a later date. Okay? Alright, see you around.